Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on similar figures. So two shapes are said to be similar if pair of corresponding angles are equal and also pair of corresponding sides are in the same proportion. The idea is that if two shapes are similar, one's just a bigger version of the other. So we could take this triangle here and we could just blow it up. We increase it proportionally. So these two are like the same shape, but not necessarily the same size. So mathematically, to be similar, pairs of corresponding angles will need to be equal. So this angle at the top would be equal in both cases. This angle and this angle would be equal, and also these angles. So that's the first condition, pairs of corresponding angles equal. Now the second is pairs of corresponding sides must be in the same proportion. So I've written some side lengths here, but to understand the concept of being in the same proportion, we need to know about scale factors. So the scale factor between two shapes is the side in the larger shape divided by its corresponding side in the smaller shape. So for these two shapes here, the two longer sides correspond to each other. So here, 10 over 5 is the scale factor of those sides. And the middle sides correspond to each other, 8 over 4. And then the shorter sides correspond to each other. So in this case, 10 over 5, 8 over 4, 6 over 3, they all equal the same thing of 2. What does this all mean? So the scale factor between this shape and this shape is 2. This means that each side in the larger shape is 2 times or double the corresponding side in the smaller shape. That's what it means for sides to be in proportion. The scale factor is the same for the longer sides, for the middle sides, and the shorter sides. So we can view this as a transformation. We've taken this shape to this shape by enlarging it, transforming this shape by enlarging it. And so in this case, all sides are in the same proportion, pairs of corresponding angles are equal. That means these two shapes are similar. This is just a bigger version of this shape here. So we could do something similar here with this rectangle. Similar figures need not necessarily be triangles. So we could take this rectangle here, and instead of an enlargement, we're going to perform a reduction. So this shape is just a larger version of this shape. So because I said they're both rectangles, both of them have all four angles equal to 90 degrees. So they have pairs of corresponding angles that are equal. These two angles are equal, these two angles are equal, and so on. But not all rectangles are necessarily similar to each other. They must also have sides in the same proportion. So if I put on these side lengths, then these two shapes are similar. So they have a consistent scale factor, 15 over 10, longer side divided by longer side equals 6 over 4. Both of those are equal to 1.5. So the scale factor of this transformation is 1.5. So it's a transformation. I went from this shape to this shape. This time I reduced. I made this shape smaller. I reduced it by a factor of 1.5. So the scale factor of 1.5 means each side in the larger shape is 1.5 times its corresponding side in the smaller shape. I multiply 4 by 1.5 to get 6 and 10 by 1.5 to get 15. So let's look at another example of two shapes that are similar. So it turns out if you have any two regular shapes, they will be similar to each other. This works for hexagons, for equilateral triangles, for regular octagons, and it works for these pentagons here. Now in a previous lesson, we worked out that the angle sum of any pentagon is 540. So a regular shape means all sides and all angles are equal. So if you have a regular pentagon, each angle will be 540 over 5, which is 108 degrees. That means each of these angles here is equal to 108 degrees. But see, this is true of any regular pentagon. These angles here must also be 108 degrees if the shape is regular. So the first condition on the previous slide is satisfied here. All of these angles are equal. Pairs of corresponding angles are equal. These two are equal, these two are equal, and so on. So what about sides being in proportion? Well, let's say that the side length of this was 4. So each side is 4. Let's say the side in the larger shape was 7. Each side was 7. Well, then the scale factor here is consistent. It's 7 over 4, which is 1.75. So I'm going to times this by 1.75 to get this side. But it'd be the same here. This is 4, and this would also be 7. So you can see each time I'm timesing something by 4 to get to 7. I'm timesing the side in the smaller shape by the same number to get the side in the larger shape. So that's why all sides are in proportion. And that would work, for example, with something like equilateral triangles. All angles equal to 60 degrees, and you have exactly the same logic that I went through. That's why regular shapes are always similar. So now let's look at an example of some shapes that are not similar. So let's look first at this pair of shapes here. Well, both of these are rectangles. It turns out, however, they are not similar. So you can't just say, oh yeah, because two shapes are both rectangles, they must be similar. Now, two rectangles will always have the same angles equal. Both of them have all 4 right angles, so pairs of corresponding angles are equal, those two are equal, these two are equal, and so on. The first condition is satisfied. The second condition, however, is not satisfied. The sides here are not in proportion. So the scale factor from the longer side to the longer side is 2. 12 over 6 is 2. The longer side in the big shape is double the longer side in the smaller shape. But of course here, the scale factor doesn't work. It's not 2. To go from 5 to 3, you'd actually have to times by 3 over 5. The point is, this side is double this side. But this side is definitely not double that side. The sides are not in proportion. Therefore, these shapes are not similar. So the idea is this shape here is not just a bigger version of this shape here. They're sort of totally different rectangles. So that's why it's important when you're determining similarity, you look at both of the conditions on the first slide. Pairs of corresponding angles need to be equal, and also pairs of corresponding sides in the same proportion. So over here we have the opposite case. We have a situation where sides are in proportion, but angles are not equal. So the sides are in proportion because the scale factor is consistent. The longer side here is double the longer side there. 10 over 5 is equal to 2. So that's the scale factor of those sides. The scale factor of these sides, 8 over 4, is also 2. The sides are in proportion because each side in the bigger shape is double its corresponding side in the smaller shape. So the second condition is satisfied, but the first is not. They don't have the same angles. Pairs of corresponding angles aren't equal. 90 degrees doesn't equal 100 degrees, 90 degrees doesn't equal 80 degrees. Now that makes a lot more sense for this shape. For these shapes, why they would not be similar. The top shape is a parallelogram and the bottom shape is a rectangle. They're not even the same shape. So if they're not the same shape, there's no way they'd be similar. This shape isn't just a bigger version of this one. They're totally different shapes. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.